So in our last lecture, we proved Lagrange's theorem. So let us recall what is going on. We have a group G, and H is a subgroup of G, and X is an element of G. So we define the left coset, XH, is everything, it's the set of elements of the form X times H, where H runs through all the elements of the subgroup H. This is if the group is written multiplicatively. And G mod H is the set of all left cosets. So this is the set of all subsets of G of the form X times H, where X runs through G. And what we proved about left cosets is that they partition the group. What does it mean to say they partition the group? It means it's a collection of sets. Every element in the group is in one of the sets and exactly one of the sets. So we notice that E is in H implies that X times E is in the left coset. X times E is X. So every element of the group belongs to some coset. And we also proved that these sets are pairwise disjoint. If X and Y are elements of the group and XH intersects YH in at least one element, so the intersection is not empty, then in fact, these two sets are exactly the same. So when you have the group G, it's partitioned into these various left cosets, and there can be a finite or an infinite number of them. The index of H in G is the number, which is usually denoted as G colon H in square brackets, is the number of left cosets. So this index is exactly the cardinality of the set of left cosets. We also define right cosets. So the right coset HX, X is on the right, is the set of everything, that can be written as H times X, where H runs through all the elements in the subgroup. And again, the right cosets partition the group G. And we write H slash G is the set of all the right cosets. And the great theorem that I proved in the previous lecture is Lagrange's theorem. It says that if G is a finite group, then the cardinality of G, and H is a subgroup, G is a finite group, and H a subgroup, then the cardinality of G is the cardinality of H, or the order of H, times the index of G in H. And this is true whether we look at left cosets or right cosets. So this is really a fundamental identity in group theory. And this has a lot of corollaries. One corollary is, because these are integers, this says this number factors into this times this. So the order of a subgroup divides the order of the group. Always. Let's look at some examples of this. Suppose we take a finite cyclic group of order 6. So let's say G is equal to the identity x, x squared, x cubed, x to the 4th, x to the 5th, with multiplication, and of course, x to the 6th is the identity. Suppose we let H be the subgroup consisting of E, x squared, and x to the 4th. So this is a subgroup. So the left coset EH is just E times each of these elements. It's just H. If I take the left coset XH, this is x times E squared, x times x squared, x times x to the 5th. That's x, x cubed, and x to the 5th. What do we know? The order of G is 6. The subgroup has 3 elements. The order of H is 3. That means the index, the number of left cosets, is 6 over 3 is 2. And here they are. This is one coset, and here's the other coset. Let's look at another example. Suppose we look at an example of an additive group. So in an additive group, G with subgroup H, a left coset is of the form x plus h. This means everything of the form x plus little h, where h is an h. Let's look at an example. Suppose we take G to be the integers mod 12. So these are the congruence classes. And I'll just write bars. I'll write x bar will mean x plus 12z. So I don't have to keep writing the x plus 12z. So 0, 1, 2, up to 11. This is a group with 12 elements, the 12 congruence classes. Suppose I take H to be 0, 4, and 8. So this is a subgroup. And the order of G is 12. The order of the subgroup H is 3. So how many cosets will there be? 12 over 3, or 4. So what are they? Well, we can take 0 plus H, which is just H, 0, 4, 8. we can take the coset of 1, 1 plus h. You add 1 to everything, you get 1, 5, 9. 2 plus h, you add 2 to everything, you get 2, 6, 10. And 3 plus h, you add 3 to everything, you get 3, 7, 11. So we have 4 cosets, and there they are. Let's make another observation. If the order of G is P, a prime number, then the only subgroups of G are the identity and G itself. I mean, in any group, the group is a subgroup of itself, and the set consisting just of the identity is always a subgroup. Why is there no other subgroup? So if H is any subgroup of G, then the order of H divides the order of G. But G has a prime number of elements, which means, well, what are the divisors of a prime? Just one in itself. So either the order of H is 1, in which case H is just the identity, or the order of H is P, and H is equal to the whole group. So a group with a prime number of elements has no non-trivial subgroups. And in fact, there's an important definition in group theory of what is called a simple group. A simple group is a finite group G whose only subgroups are the identity and G itself. So Lagrange's theorem implies that every group of order P, a prime, is a simple group. Let's make another observation. Suppose that G is a group and let X be an element of G, then X to the N is in G for every integer N, positive or negative. And the set H, consisting of all the powers of X, so the 0th power, we always define X to the 0 to be the identity. So you have E, X, X squared, X cubed, X inverse squared, which we write as X to the minus 2. This is a subgroup of G. So H is called the cyclic subgroup of G generated by X. And denoted often by X with sort of angular brackets around it. So for example, if G is the cyclic group of order 12, let's say it just consists of a squared up to a to the 11th. So a to the 12th is equal to the identity. And if we choose x equal to, let's say, a to the 4th, then the cyclic subgroup generated by x is the identity, x squared x, and x squared. That's e, x is a to the 4th, x squared is a to the 8th. And so this is a finite subgroup of the cyclic group. In fact, we can then say the following. If G is a cyclic group of order P, some prime number, and X is in G and X is not the identity, then X, we say, generates G. This means the cyclic group generated by X is equal to the whole group G. And why is that? Well, suppose we let H be the cyclic group generated by X. So we have E is in H, because every subgroup contains the identity. X is certainly in H. X is different from the identity. That's how we chose it. So the order of H is greater than 1. But the order of H divides the order of G, which is a prime. So therefore, the order of H is equal to the prime, which means H is equal to the whole group, because whole group is P elements. If you choose a subset of size P and a set of P elements, you have everything. Okay? So these are all nice consequences of Lagrange's theorem. Let's look at an additive example of this. So in an additive group G with an element X in the group D, the cyclic subgroup generated by X is EX, it's the multiples, and minus X minus 2X. So all positive and negative multiples of X. So suppose we take the congruence class as mod P. So this is a group with a prime number of elements. If X is in Z mod PZ and X is not 0, which means not the congruence class of 0, then X, by what we just said, X generates Z mod PZ. So let me just call this element A. If A is a congruence class, and A is not the 0 class, then A generates Z mod PZ. What does this mean? This implies that for every integer b, there exists an x such that x times the congruence class a plus pz equals b plus pz, which means ax plus pz equals b plus pz, which means ax is congruent to b mod p. That means for every b, you can solve this linear congruence. So the theorem on linear congruences with a prime modulus is a special case of Lagrange's theorem in group theory. If p is prime and a is not 0 mod p, then for every b, you can solve this congruence. There exists an x which solves that congruence. That's actually very nice. Let's go back again to the integers. So suppose m, a positive integer. So mz, the set of multiples of m, is a subgroup of z. And the set of congruence classes is just the set of left cosets, a plus mz. A equals 0, 1, 2, up to m minus 1. So for every positive integer m, we have this subgroup, the multiples of m, subgroup of z. This is the set of left cosets. That means the set of congruence classes. And there are exactly m of them. But this is important. Z mod mz is not just a set. This is a group under addition. That is, we can add congruence classes. If you have the congruence class a plus mz and the congruence class b plus mz, you can define the sum of these two congruence classes to be the congruence class a plus b plus mz. And this addition of congruence classes, which is the same as saying the addition of left cosets, makes sense, is well defined. It's a consistent definition of addition. So we can ask the following question. If we have a group G, a subgroup H, when is G mod H the set of left cosets? When is this a group? And in fact, it would be nice, so we would like to be able to multiply cosets. If we have a coset AH, we want to multiply it by a coset BH and get some other coset. And what would be a very beautiful and simple way to do it is if we could define the product of AH times BH to be the coset ABH. Let's just say we would like this kind of rule to be true. So it's a natural and basic question. For what subgroups H is G mod H, the left cosets, a group? In fact, with this multiplication of cosets. And this question has a remarkably simple answer. So I'll state the answer and then I'll prove that it all makes sense. So we have H, or let's put it like this. I'm going to make a definition. A subgroup H of a group G is called normal, a normal subgroup, if for every X in the group, the left coset and the right coset, these don't have to be the same, are equal. Okay? So it's not true in general that every left coset equals the right coset. But when it is true, the subgroup is called normal. And so I'll state a theorem which says that if H is a normal subgroup of G, then the binary operation on the set of left cosets, AH times BH equals ABH, is well defined, and G mod H is a group. So that theorem deserves a star. So if you have a group in which every left coset is a right coset, then you can multiply cosets by this rule. Now there's one simple case when this condition is satisfied, always. So if G is an abelian group, then for every X in the group, the left coset, XH, this is all elements of the form X times H for H in the subgroup. But because the group is abelian, XH is equal to HX. And this is just a definition of the right coset. So for abelian groups, every subgroup is normal. And that's exactly the example we've been looking at. The additive group of integers is abelian. So the subgroup MZ is normal. And so Z mod MZ, the additive group of congruence classes, is a group. So let's prove this big theorem, that if a subgroup is normal, you can multiply cosets. Let's begin with, so what is the problem? Why, suppose you have a coset AH. Now, it can be the case that AH is equal to, or let's say you have a coset XH. So it's all multiples of elements of H on the left by X. And suppose you have a coset YH. So this is Y times H for H in H. So it can happen certainly that so we want to know, when is XH equal to YH? We know the two cosets are either disjoint or they're identical. So if XH equals YH, that means that X, which is X times E, is in XH, which is YH, which means that X is equal to YH for some element H in the subgroup, which means that Y inverse X equals H is in the subgroup. So if XH equals YH, then Y inverse X is in the subgroup. Conversely, if X and Y have the property that Y inverse X is in H, then Y inverse X equals little h for some H in H, which means X, if I multiply on the left by Y, X is equal to Y times H. Let me call this X, H0, some particular one. So if Y inverse X is in the subgroup H, that means Y inverse X is equal to H naught for some element H naught in the subgroup. So X is Y H naught. So for all X in H, XH is Y H naught H. H naught H is an element of H. This is in YX. So this means that the whole left coset XH is contained in YH. Now, each of these implications needs a justification. So I'm saying exactly what the reason is for every one of these statements, but it really takes a lot of thinking, careful thinking, step by step on your part to make sure you understand why each of these conditions is true. So if Y inverse X is in H, then HX, this coset is contained in this coset. Also, if Y inverse X is in H and H is a subgroup, then the inverse of Y inverse X is in H. And the inverse of Y inverse X is X inverse Y. So X inverse Y is in the subgroup, which means YH is contained in XH. So if XH is contained in YH and YH is contained in XH, then XH equals YH. So we now have a proof, if you like, of the following lemma. Two cosets are equal if and only if Y inverse X is in H. Okay. Now, let's see if that's enough to prove that that multiplication of normal subgroups is well defined. So what is the problem? The problem is, suppose we have a coset A1H equal to the coset A2H. And we have a coset B1H equal to the coset B2H. So we must prove, in order for multiplication of cosets to be defined properly, that A1H times B1H is the same as A2H times B2H. This is what we have to prove. Another way of saying that is that must prove that A1B1H equals A2B2H. But this is true if and only if let's go back and remember the condition. So XH equals YH if and only if Y inverse X is in H. So this equals this if and only if A2B2 inverse A1B1 is in H. But what is A2, B2 inverse? This is B2 inverse, A2 inverse times A1, B1. Is that an H? Good question. Well, what do we know? So I can also write this as B2 inverse, A2 inverse A1, B1. Is this an H? So what I know is that A1H equal A2H means that A2 inverse A1 is some element, I'll call it H0, doesn't matter, H0, or some H0 is in H. So this is actually equal to B2 inverse A2 minus 1 times H0 B1. Now I haven't used the fact that H is normal. So if H is a normal subgroup, then the coset B1H equals the left coset equals the right coset HB1. So what do we know? Well, H0 B1 is in HB1, which is the same as B1H. The right coset equals the left coset, which means H0 B1 is actually B1 H1 for some H1 in H. So this H0 B1 I can write as B1 H1. So what I have, let's take this down here. B2 inverse H0 B1 is B2 inverse B1 H1. But B2 inverse B1 is an element of H. So just as A1H equal A2H implies this, B1H equal B2H implies B2 inverse B1 is some element H2 in H. So this is H2H1, which is in H. This is a product of elements in H. So we're done. Let me just go through that quickly just to review this. I want to show that multiplication of cosets for a normal subgroup is well defined. What does that mean? It means if I can represent a coset in different ways. So let's say that A1H and A2H are the same coset, and B1H and B2H are the same coset. Now, what that means, if I want to prove that when I multiply A1H and B1H, I get exactly the same coset as when I multiply A2H and B2H, because these are the same. This product is A1, B1H. This product is A2, B2H. So these are equal if and only if A2, B2 inverse A1, B1 is an H. This is B2 inverse A2 inverse A1, B1. I have to prove that's an H. But what I have here in the middle, A2 inverse A1, I know that's an H, because A1H equals A2H. So this is just some element H0 in the subgroup H. So I can write this like this. Now I use the fact that we have a normal subgroup. H0 times B1 is B1 times some element H1 and H. So if I plug in here, B2 inverse H0 B1 is B2 inverse B1 H1. H is an H. I'm done. I win. That's pretty good. Okay, I'll continue this in the next lecture.